So we're going to discuss the common ion effect. Essentially, if you have a solution that contains an ion, and maybe you are trying to create a precipitate, but one of those ions that is in the precipitate is actually in the solution, it makes it harder to dissolve that compound. So let's just say that I have silver chloride. So I have silver chloride in a solution, and I'm trying to dissolve it. So if I were to have silver ions already present in that solution, that makes this compound less soluble. So if I were to take silver chloride and then put it into a solution that has silver nitrate that has the silver ion, that means that it's going to be less soluble. So you're going to have less of that silver chloride dissolve into that solution. So if I were to also have that silver chloride and I put it into a solution of potassium chloride, well, if the chloride is present, again, it's going to make this compound less soluble. So if you already have that ion present, that impacts the solubility. Now, it doesn't impact the Ksp value, but it does impact how much will dissolve. So given that the Ksp for silver chloride is 1.58 times 10 to the negative 10, calculate the molar solubility of silver chloride in pure water, a solution that has the silver ion concentration of this, and then a 0.025 molar solution of KCl. So let's go ahead and just set it up here. So I'm looking at silver chloride, and I want to dissolve it and make my ions. So I know that the Ksp value is equal to 1.58 times 10 to the negative 10 here. I also know that Ksp is equal to the concentration of each of these ions multiplied together, and of course to the first power because it's a 1-to-1 ratio. So the first question was asking about the solubility in just pure water. Okay, so there are no silver ions present or chloride ions present. Well, what we're going to do, we have the Ksp value. We're trying to find the molar solubility, so we need to find little x. So we're going to set up an ice table. So initially there's 0 and 0 because it's just water. And we're going to add 1x for each of these. Well, if the Ksp is that, I'm really just solving for little x. So my Ksp is 1.58 times 10 to the negative 10. That's equal to x multiplied by x, so x squared. Take the square root to get x by itself. You're going to get 0.906. So if I have 1 liter of water, I'm going to dissolve 0.906 moles. So let's see how this is impacted if I put it into a solution of silver. So the silver initially has a concentration of 5.5 times 10 to the negative third. So we're doing the same thing. It's just now it's not starting at 0. So this will be starting at 0 because I don't have any chloride ions present, and it's still the same process. So if I were to dissolve it, how much comes out? So this is going to be 5.5 times 10 to the negative third plus x, and then also x. Okay, so now we can plug that into the Ksp expression and do the same exact thing. It's just now we're not starting with 0. So Ksp is 1.58 times 10 to the negative 10, and that's equal to 5.5 times 10 to the negative third plus x times x. Well, K is very small. That means I can assume x is very small. So if x is very small, I can approximate and take that out and not have to deal with quadratic because I don't want to do that. So it's going to be 1.58 times 10 to the negative 10. And that's equal to 5.5 times 10 to the negative third times x. So solve for x, and you're going to get 0.0000000029. So, and as you can see, the solubility went down, went way down, because I already have some of that ion present. So let's do that again for the chloride ion. Okay, so I have KCl. Same process, have an ice table. This, the silver will be 0 this time, but this will be 0.025 because it's KCl. So for every 1 KCl that I have, I'm going to make 1 chloride ion. So I should have the same concentration. So again, plus x, and then this is going to be 0.025x plus x. So again, I know that my Ksp is very, very small. So if my K is very small, I can assume that x is very small, and if you add or subtract by a very, very small number, you can pretty much leave it out. So I have 0.025 plus x, but I leave that out, times x. So now solve for x, and you should get 0.000000006 moles per liter. And again, if I have something present, like if I have this much present, it makes the molar solubility go down. So check to see if it's just pure water, it's just going to be the normal setup. But if you already have that ion present in the solution, you need to account for that, and you should see the molar solubility go down because of that.